I'm sure from your prior studies in statistics you'll have heard of a confidence interval, but it's a concept which is widely spoken about but also often misunderstood. So a confidence interval is a range of values for the estimate of an unknown parameter, and it's associated with a confidence level. Now this confidence level says this is the long run proportion of confidence intervals generated in this way that would cover or contain the true value of the parameter. So if I follow my procedure, I obtain a confidence interval. I do the same procedure again with a different sample, I get a different confidence interval. Same procedure again with a different sample, I get another confidence interval. So if I take, for example, 95% confidence level, then 95% of these intervals should cover or contain the true value of the parameter. So as I said just at the top here, it's easy to misunderstand these, and you will often hear them misapplied or poorly explained. I just want to give a couple of explanations of what a confidence interval is not. If I get a 95% confidence interval, it does not mean that 95% of my observations will be in that interval. It doesn't mean that there is a 95% chance that the true parameter value lies in that interval. The parameter value is what the parameter value is. It's whether or not my interval, which I'm generating, which is random, based on the random sampling, will cover that true value. So what we can do is we can apply the central limit theorem to construct confidence intervals. Central limit theorem simply says that if I'm sampling from any distribution which has finite mean and finite variance, then taking a load of independent realizations from my distribution and working out the sample mean, then for large n, my sample means calculated over n samples will be approximately normally distributed. So what this means is if I want a confidence interval, let's say 95% confidence interval, if I know the variance and I want a symmetric confidence interval for the mean, then I can say, well, my confidence interval for the mean will be the sample mean plus or minus the Z score for the appropriate confidence interval. So let's say I want a 95% confidence interval. My Z percentiles, the standard normal, would be the 2.5 percentile and the 97.5 percentile, because that's the symmetric 95% around the mean. In that case, the Z score is 1.96. That number may be familiar to you. So the symmetric confidence interval would be the sample mean plus or minus, in this case, 1.96 times the square root of my population variance sigma squared over the sample size n. A situation that we're more commonly in is where we don't know the population variance. So I can have a set of observations, but I'm trying to characterize what I believe about the population mean from this sample, but I'm also trying to capture the variability as well. Well, the best that I can do, or one thing I can do, is to try and estimate the population variance using the sample variance. Well, we showed already in the video introducing bias that in fact using the second central sample moment as an estimator actually produced a biased estimate, not by much, by this factor of multiplication by 1 over n, but particularly for small samples, that bias can be significant. So if I want an unbiased estimator, I'd have to correct by this factor of n over n minus 1. Let's say we work out the second central sample moment and multiply it by n over n minus 1 and say, well, I don't know what sigma squared is, but I've got an unbiased estimate of it. We saw previously that for a linear regression model, even one with multiple slope parameters, if the residuals are independent and normally distributed with some constant variance, then the SST, the total sum of squares around the mean, would be approximately a chi-squared distribution, or sigma squared, times a chi-squared variable with n minus 1 degrees of freedom when I had n observations. You would think maybe chi-squared with n degrees of freedom if I'm adding n independent squared normals, but the constraint of them having mean y bar removes one of those degrees of freedom. Similarly, I can say the same about the x's, where they, of course, are constrained to still have mean x bar. So it does mean that if I'm trying to estimate the sigma squared parameter with an estimate of it, in this case 1 over n times the sum of the xi minus x bar squared, then what I've got is I've got something which is like a normal on the top and the square root of a chi-squared variable over n in the denominator. We've already seen that the ratio of a normal variable, a standard normal, to the square root of a chi-squared n minus 1 variable divided by its own degrees of freedom is a t variable with n minus 1 degrees of freedom. So what this does mean is if I know the population variance, then I've got this z percentile in there. And if I don't, then I've got to replace it with a t percentile. So this looks exactly the same, but I've got a different formula for the confidence interval if I know the population variance and I'm using that, versus if I'm using the same observations to try and describe my uncertainty about the population mean, where I don't know the variance, and I'm having to use the same set of observations to calculate or estimate the population mean and the variance. Now, when I've got this regression model which has multiple slopes in there, we said that the sum of the squares around the mean y bar would be proportional to a chi-squared with n minus 1 degrees of freedom, and the sum of squares around the model, where I've got y hat as my estimate, where I've estimated another k parameters, in this case the k slopes of the model, would be proportional to a chi-squared with n minus k minus 1 degrees of freedom. Rather than fixing one parameter, the mean, I'm fixing the mean and the k slopes. So what this does mean is that if I just think of the simple case where I only have one slope, the simple linear regression model, then in fact the SSE, the sum of squared errors around the mean, should be chi-squared or proportional to chi-squared with n minus 2 degrees of freedom. So I take the expectation of this. The expectation of a chi-squared is its own degrees of freedom. So in this case, n minus 2 multiplied by the sigma squared. If I plug all this through, then I can show that an estimator theta hat squared can be estimated by the residual squared over n minus 2, and that will be an unbiased estimator of sigma squared. Now again, pause this if you want to go through the details. I'm just going to present this fairly quickly to avoid talking you through every term. But we've seen that we've seen the variance of the estimators alpha hat and beta hat in this simple linear regression model. I want the confidence intervals around those where I don't know sigma squared and I'm having to estimate it from sample. Again, I've just substituted through with the estimate. It gets very messy, but again, I'm using a t-statistic just with very messy estimates of what these estimates of the standard error are.